Alright, welcome back to the AI Research Roundup. I am your host, Alex. Today we're looking at a fascinating paper from NVIDIA called Cosmos-Reason1, From Physical Common Sense to Embodied Reasoning. The goal here is to build what they call physical AI, systems that can truly understand the physical world to make decisions, like what a robot should do next. To achieve this, they built a special knowledge base using an ontology, which is a formal way to represent concepts, in this case, about space, time, and physics. This helps the AI with embodied reasoning, basically thinking and planning as if it has a physical body. And what's great is that this isn't just a paper. They've also released a full GitHub repository. It has the Cosmos-Reason1 models, the benchmarks, and their entire toolchain for training. This includes tools for supervised fine-tuning, which is a way to specialize a model with new examples, and also for reinforcement learning, where the model learns from feedback on its actions. It's really a complete package for researchers. So this first figure really lays out the entire ecosystem. You can see it's broken into 4 key pillars. First is the model itself. It has a vision encoder, which is the part that processes video frames, a projector, which acts as a bridge, and a pre-trained LLM. This setup makes it a multimodal model because it handles both visual data and language. Then, you see the training stages we just discussed, the ontologies that structure the knowledge, and finally, the benchmarks used to test everything. It's a really clear end-to-end view of their whole approach. Okay, so let's zoom in on that physical common sense ontology I mentioned. This pie chart breaks it down for us. You can see it's built on 3 core concepts: space, time, and fundamental physics. And around these cores, we have 16 more specific subcategories. For example, under space, you have affordance, which is about what an object lets you do, like a cup affords drinking. And under physics, they include concepts like object permanence, the idea that things exist even when hidden, and even anti-physics, which likely helps the model learn what is impossible. So this table gives us the details behind those 16 categories we just saw. It defines the specific capability the AI should have for each one. For example, under space, the affordance subcategory means the model should understand how things like humans or robots can interact with an object. Under time, causality is about determining if one event causes another. And in the physics section, it gets really detailed, covering everything from basic mechanics like gravity and friction to even identifying anti-physics, like spotting situations that defy the laws of nature. It's a comprehensive list of reasoning skills. Now, building on that foundation of physical common sense, we have the second ontology for embodied reasoning. This table shows how those abstract concepts translate into actions for different agents. It's broken down into 4 key capabilities, like process complex sensory inputs and predict action effects. And it shows examples for both natural agents, like humans and animals, and for robotic systems, like robot arms or self-driving cars. For instance, predicting action effects is like a dog estimating where a ball will land, or a robot arm compensating for an object's weight before lifting it. Alright, so after laying out, though, what those ontologies for knowledge and action, this diagram shows us the how. This is the actual architecture of the Cosmos-Reason1 model. On the left, it takes in an input video and a text prompt. The video is processed by the vision encoder and projector we mentioned, turning it into video tokens. These are then combined with the text tokens. This combined information then flows into the LLM itself. You can see they show 2 versions. One uses standard self-attention layers, which help the model weigh the importance of different inputs, and MLP layers. The other is a hybrid model that adds a Mamba layer, which is a more recent architecture designed to handle long sequences like video very efficiently. Finally, you see the output, a clear chain of thought where the model reasons about what it sees before generating the final action. Okay, and this table gives us the nitty-gritty technical specs for those 2 model versions we just saw, the Cosmos-Reason1 7B and the much larger 56B. You can see how they differ in each component: the vision encoder, the projector that connects vision to language, and the LLM backbone itself. The biggest difference is in that backbone. The 7B model is a standard transformer, while the 56B model uses that Mamba-MLP-Transformer hybrid. It's also much deeper, with 118 layers and 64 attention heads, which help it focus on many different input details at once. And this diagram here gives us a visual breakdown of that hybrid Mamba-MLP-Transformer backbone we just saw in the specs for the 56B model. At the top, it lays out the two fundamental building blocks. You have the traditional transformer block with its self-attention and MLP layers, and then the alternating Mamba-MLP module. This Mamba module, as you can see, swaps out that self-attention for Mamba layers, which, as we mentioned, are designed to be more efficient for long sequences like video. The bottom part of the diagram then shows how the full backbone is constructed by stacking these different blocks in a very specific, alternating sequence to build out the deep network. Putting it all together, what we're seeing with Cosmos-Reason1 is a really fascinating approach to embodied AI. By combining that classic transformer architecture with the newer, more efficient Mamba layers, and training on this rich mix of data, the researchers are creating an agent that doesn't just see, it reasons about the physical world. This is a big step toward robots that can operate with genuine common sense. Well, that's all the time we have for today. Thanks for joining me on the AI Research Roundup. I'm your host, Alex,